Welcome to Quant Concepts. This is a quick 10-minute lecture on the fundamentals of hypothesis testing. This is a crucial topic in any study of statistics and quantitative methods. I assume the audience has no background in statistics. So let's say you hang out with your friend Sam one day, and you both decide to go bowling. And while you're driving to the bowling alley with Sam, he keeps on saying, "Mate, my bowling average is so good, I've got a long-term average of 150, rah rah rah." Now, in case you don't know, 150 is an excellent average for bowling. It means Sam is a very, very good bowler. So let's say you play your 3 games of bowling with Sam, and over the 3 games, Sam's average score is a dismal 40. Now, in such a scenario, do you believe him? Do you believe Sam's claim that his long-term bowling average is 150? And more importantly, is Sam a dodgy friend? You would probably not believe him. Why is this? Because if Sam's long-term average really is 150, then this means he's a very good bowler. And if he is a very good bowler, it is highly unlikely that he would have scored a miserable average of 40 over your 3 games with him. Now, let's rewind the clock a little bit, and say you play the 3 games with Sam, but this time his average over the 3 games is 140. Now, in this case, do you believe him? You'd be much more likely to believe Sam in the second scenario, yeah? Because scoring 140 is very close to his claimed long-term average score of 150. On top of that, if 150 is his long-term average, it doesn't necessarily mean that he will score 150 every game. What it does mean is that Sam will score an average of 150 over many games. Maybe Sam underperformed today because he had a bad day. Maybe he didn't like the bowling ball. Or maybe he met a pretty girl in the morning and his love struck. Who knows? There are a million reasons why he may have underperformed. But the main point we're trying to get at is that you are more likely to believe Sam's claim, as 140 is very close to his claimed average of 150. So we can see these 2 extreme cases. One where you will be unlikely to believe Sam and call him a liar, and another where you'll be likely to believe him and still be friends. Now, can you tell me, at what point between 40 and 140 do you make the decision to believe Sam or not? Well, this is actually quite subjective, but in your mind, you will have a cutoff score that you will use to determine whether Sam's claim is correct or not. For example, you may tell yourself that if Sam scores an average over our 3 games that is below 120, I won't believe his claim. However, if he does score an average over our 3 games that is above 120, I will believe him. This is quite intuitive. So Sam makes a claim that his long-term bowling average is 150, and if his average over the 3 games falls below a particular value, such as 120, we will reject his claim. Easy enough, yeah? Now, let's have a look at a possible probability distribution of Sam's bowling scores, assuming that his claim is correct. Because at the end of the day, Sam is your friend. You will give him the benefit of the doubt until proven otherwise. Now, this is known as a probability density function, which we will discuss in more detail later in the lecture. All you need to know for now is that the x-axis contains all possible values for Sam's average bowling scores for your 3 games with him, and the y-axis contains probabilities. Therefore, the higher the graph at a particular bowling score, the higher the probability of that bowling score occurring. Likewise, the lower the graph at a particular score, the lower the probability of that score occurring. Okay, so given that Sam's claim is correct and that his long-term average is 150, then we would expect his bowling scores to be very close to 150. Hence, the graph peaks at 150. This means that we would expect, with a high probability, that Sam's bowling scores will be close to 150, assuming his claim is correct. Furthermore, you can also see that values that are far from 150 have a lower probability of occurring, as the graph is lower at scores further away from 150. This makes sense, because if Sam's average really is 150 and he really is a good bowler, then there should be a low probability that he scores very poorly in bowling. Now, remember our cutoff value is 120. That is, you will believe Sam if he scores over 120 in your 3 games with him, and you won't believe him otherwise. The shaded region is known as a rejection region. If Sam's average score over his 3 games with you falls below 120, you will reject his claim. Let's picture another scenario. It's your mum's birthday, and you decide to take her out bowling. And in the car, whilst driving to the bowling alley, your mum tells you, "Honey, did you know that I'm an excellent bowler? In fact, dear, my long-term average for bowling is 150. Interesting. So you play 3 games of bowling with your beloved mother, and her average score over the 3 games is a depressing 40. Now, what do you do? Do you believe your own mum's claim that her long-term average is 150? Or do you call your own mother a liar? Well, it's a tough situation. Firstly, it's highly unlikely that her claim is correct. However, it is possible she may be just having a really bad day. Now, you're more likely to give your mum the benefit of the doubt than you are to Sam, right? Because the last thing you want to do is to call your mum a liar when in fact she really was just having a bad day. Now that's just plain cruel. So, when rejecting your mum's claim of having a long-term average of 150, you want to be really sure that she's lying before you do so. So, what do you do if you want to be more sure that a claim is false before rejecting it? Simple. We simply use a lower cutoff value. For example, you may have told yourself that you will believe Sam if his average score over the 3 games with you is above 120. As you love your mum and are willing to give her the benefit of the doubt, you may tell yourself that you will believe your mum's claim if her average over the 3 games with you is above 50. So your cutoff value for Sam is 120, and your cutoff value for your mum is only 50. Calling Sam a liar is no big deal. He lies all the time, so you have a higher cutoff value for him. But calling your mum a liar is a massive deal, so you have to be very sure she's lying before you do so. So you have a lower cutoff value for her. Besides, you never really like Sam anyway, and your mum's cooking you a nice dinner tonight, even though it is her birthday, you lazy bugger. So the probability distribution of your mum's bowling scores will look something like this. In this case, however, notice that the cutoff value is only 50, whereas for Sam it was 120. Therefore, the shaded region, or the rejection region, is much smaller in your mum's case. What the smaller rejection region signifies is that you are less likely to call your mum a liar when she is in fact telling you the truth, because doing so will send you straight to hell. In the case for Sam, the repercussions of calling him a liar when he is in fact telling you the truth is not so harsh, so his rejection region is of a larger size. Hence, the size of the rejection region and how far the cutoff value is from the claimed average is determined by you, the researcher. It depends on how sure you want to be when rejecting the claim. We can see that the smaller the rejection region, the more sure we are when rejecting the claim. Now, time for some statistical jargon. If you've understood the lecture so far, then you're already miles ahead in learning hypothesis testing. All we need to do now is to add the statistical names to the ideas that we've just discussed. The null hypothesis is the claim we are trying to test. It is denoted by H0. In our particular case, we are trying to test Sam's claim that his long-term average bowling score is 150. So the null hypothesis is that Sam's long-term bowling average is equal to 150. The alternate hypothesis, usually denoted by H1, is the counterclaim. That is, what must be true if the null hypothesis is false. So, in our little example, the alternate hypothesis is that Sam's long-term bowling average is below 150, and he is a liar and a dodgy friend. The sample statistic, usually denoted by X, is the observed sample estimate that we use to determine whether the null hypothesis is false or not. In this case, the sample statistic is Sam's average score for the 3 games you played with him. The critical value is simply the cutoff value you assign to the sample statistic to determine whether the null hypothesis or claim is rejected or not. In our example, the critical value is 120. As you tell yourself that if Sam's average score for the 3 games you play with him is below 120, you will reject his claim. Finally, the significance level measures how sure you want to be when rejecting the null hypothesis. The smaller the significance level, the more sure you are when rejecting the null hypothesis, and the smaller the rejection region. So, in your mum's case, you will use a smaller significance level to determine if her claim is false or not. For Sam's case, you are willing to use a larger significance level. Thank you for listening to Quant Concepts Education. Come and visit us at www.quant-concepts.com.